A decimal number is, for example, a number of the form 12.345 or 0.333, and also, for example, pi. It's 3, 1, 4, 1, 5, infinitely many decimals. So this is a shorthand, meaning if you keep the first part, we have seen that you can express it in base 10 in the positional system. So this means 1, 10, 2 ones, and then you continue. So you have 3 tenths, 4 hundredths, and 5 thousandths. So that's the meaning of a decimal number. You continue from power tenths to tenths of negative powers, because you can write this as -1, 10 to the power of -2, 10 to the power of -3. So decimal number is continuing into negative powers of 10. For example, if you have a fraction as 13/4, how can you write it as a decimal number? You can use division algorithm. So if we write it as a division algorithm, we have 13 divided by 4. Then how many times does 4 go in 13? It goes 3 times. And 3 times 14 is 12. With the remainder of 1. Now we see that we don't have any digits left. But we don't have a remainder of 0. Meaning that this doesn't go up exactly. But then we can continue going for decimals numbers. So how many tenths? Let's see, now we have one single, and one single are 10 tenths. So 10 tenths. How many tenths can we divide up among 4 people? 10 tenths among 4 people. And each person can get 2 tenths. And how much is the remaining then? 2 times 4 is 8 tenths. So it's remaining 2 tenths. And still we don't have a 0 in the remainder. But we can change these tenths to hundredths. So 2 tenths is 2 hundredths, 20 hundredths. And how many hundredths, if you divide up among 4 people, how many hundredths do we get if you divide up 20 hundredths? Then we get 5. So 5 among 4 people, that's 20. So now we get 0, meaning that the answer to this division is 3.25. So we can write this as a decimal number, 3.25. But then there are other fractions or divisions that will never stop. For example, if we try to write 1/3 as a decimal number, then we have to answer how many times does 3 go in 1? 0 times. And if we make the calculation here, we get 1. Now we have to go to tenths, and we transform 1 single to 10 tenths. So how many tenths among 3 people? Then we can divide up to 3 parts. So 3 times 3 is 9. Then we have 1 tenth left. And if we now change this to hundredths, so we have 10 hundredths, how many do we get each then if you divide up among 3? And again we get 3, because we see that we're repeating itself now here. So we will have the same pattern. 3 times 3 is 9. And we get 1, and we change it to thousandths. We will see this pattern will repeat itself in infinity. So we will get infinite number many 3s here. So we can write this as this. So we see that if it repeats itself here, we will get infinitely many decimals. If it repeats itself and don't go to 0. In the same way, using the division algorithm, we can see that, for example, 1/8 can be written as 0.125. 1/6 can be written as 0.1, infinitely many sixes. Because you can notice here that 1/6 is a half of a third. If we divide each number here, then we get 1.6666. But you can also use the division algorithm. And 1/7, then we have a much longer repeated. The division algorithm will repeat itself in more steps after many more steps. So we will have this periodic sequence. And for example, last example, 1, 2, 3, 4, 1234 divided by 130. Then that would be 949. And firstly, then there will start to be a repeating decimal sequence. So we have like that. And for a fraction, we will always have a finite number of decimals, because if it ends up with 0, we would have a finite. But if it does not end up in 0, the remainder here, then after a while it must repeat itself, because there are only 10 or 9 if we skip the 0, 9 different remainders we can get. So after a while we must go back to some we had before, and then the sequence will start to repeat itself. So we always have, if I have a fraction, I have a finite number of decimals, or is infinitely many where it repeats itself. And now we look at the opposite. Let's say, for example, if I have 1.23, then I know, of course, I can write this as a fraction. Since it's only a finite number of decimals, I can write it like this. So I can transform it to a fraction. But for example, if I have 0.33, infinitely many threes, I can't do it that way, because they're infinitely many, so I can't divide it with infinitely many zeros here. So in this case, we have to do something different. So let's take an example of a decimal number we want to write as a fraction. So let us take, for example, this one. Then there is a method for arriving at that. Let's call this number x, just for simplicity. Okay, now we want to get the decimal number. In the method, we want to get the decimal number, or the decimal sign here and here, at the start and the end of the repeating sequence. So how do we get it there? We multiply by 10 to the 4th. So if we multiply by 10,000, we will get the decimal number here. So we repeat our number that we call x with that. And to get in the last step, how do we do then? Then we can multiply it by 10 to 8th to move it 8 steps. What happens now if we take 10 to the 8th x minus 10 to the 4th x? Then we will have, first we will have this long sequence. So this is the number where we multiply the decimal sign to the end. And then we will have our repeating sequence. And then we take away where we multiply the decimal sign to the start. That will be then we will have our repeating sequence here. And now we see that when we subtract these two numbers, these periodic sequences will cancel. So we only have these two numbers, integers, in a subtraction. So if I now do this subtraction of these two integers, for example using subtraction algorithm, then I will get the answer 1, 2, 5, 7, 8, 5, 8, 1, 5, 9. Okay, so now we have arrived at this result, taking this and this. So this is a method. We multiply the decimal sign to the end and to the start of a repeating sequence, and then we take the difference between these two. Then we will arrive at an integer, since these cancel the decimal sequences. Then we work with this part. How can we rewrite this? We can factor out our x. So we can factor out x. And how much is this one? This is 1 followed by 8 zeros minus 1 followed by 4 zeros. So how much is that? Then that will be 9, 9, 9, 9, 0, 0, 0, 0 times x. And now, on the one hand, we have this, and that's equal to this on the other hand. But now we see that we can, if we divide this by this number on both sides, we will get out x. So we will have that, we will have our number x, which was the number we were looking for to have as a fraction. And x is of course by shorthand for this decimal sequence we wanted to write as a fraction. So now we see here we have written our repeating decimal sequence here, our number as a repeating decimal sequence infinitely long. We're written it as a fraction. And this is the method. This method always works if we have a repeating periodic sequence. So we can always write it as a fraction. Now we want to see how it works when we calculate with decimal numbers. And then it can be good to have these memory rules for decimal numbers. For example, if you have 123.4567. So let's say we want to multiply it by 1000. Then we know the memory rule, as we already used, that we can move this 3 steps, since we have 3 zeros. So we move the decimal sign 3 steps. In the same way, we can move the decimal sign to the left if we instead multiply it by tenths or hundreds. For example, if I multiply it by 10 to the minus 2, and now we have to remember that 10 to the minus 2 is 1/100th. And then we just move the decimal signs 2 steps to the left instead. So this will be 1.234567. So this is a useful memory rule. Sometimes if you want to use this rule, you have to add on some zeros to be able to use it. For example, this one, we want to move the decimal signs 3 steps to the left, but there is no digit here. But since a number is, we can always put some zeros in the start, so I can add some zeros at the start. It doesn't change the value of my number. And now I can use the rule 1, 2, 3. So this will be like that. So I can always use this memory rule. But now we can ask ourselves, why does this work? Why does this memory rule work? So let us do that, show that why it works with an example. So let us take, for example, this decimal number. And we multiply it by 10 to the power of 3. So now we want to show that we will get this result, that this will be that moving these 3 steps. And if we write this as in our base 10 positional system, this would be 1 plus 2/10. But let's instead write a tenth as 10 minus 1. and then we have 3 times 10 to the minus 2, 4 times 10 to the minus 3, and 5 times 10 to the minus 4. So now we have written that in the base 10 positional system, extending to decimal numbers. But now we can use a rule for multiplying sums. So this needs to be multiplied in here, all combinations. So if we do that, we will get 1 times 10 to the third, 10, and then we have 10 to the minus 1 times 10 to the third, and that will be 10 to the second. Then we have 3, 10 to the minus 2, and 3, then we have 10 to the 1. And then we will have 4, and these will cancel, so we just give 1. And then we have 5, 10 to the minus 1. But now we see here, there's a shorthand for this, since we can write this as a decimal. This is just written in base 10. So this is 1, 2, 3, 4, and then we come to the decimals, 0.5. So we see just working this base 10 and using calculational rules, then we have seen that we arrive at this rule of thumb. So in practice, this has moved 3 steps now, but of course we have done it without using the memory rule. So that's you can show how it works. And let us now look at if we want to add larger numbers, more digits, then it's useful to use algorithms, the standard algorithms. And for addition and subtraction, there is nothing really new happening. So for example, let's say we want to add 2 numbers here. Then there's nothing new, we just place them vertically with the same base 10 representation under each other. So first adding thousands, we have 14 thousands. And we can exchange 1,000, 10 thousands to 100th. And then we have 11 here. 10, 13. And here we have 10 tenths, and that's equal to 1 whole. And then we get 3, 1. And then we just move down the decimal. So this is just the normal way you would expect it to work. And then, for example, we can do subtraction. So if you just take 2 numbers here. 8 minus 6, 2. Or what we are really doing is 8 thousandths minus 6 thousandths is 2 thousandths. 5 hundredths minus 7 hundredths, that's not possible. So we exchange 1 tenth to 10 hundredths. So we have 15 hundredths minus 7 hundredths, that's 8. And here we can't do this subtraction. So if we exchange 1 whole to 10 tenths, then we have 11 minus 9, that's 2. And now we're going to do the whole numbers. So 4 minus 3 is 1. So this is just what you would expect. You just have to keep the decimal sign in the right place. When it comes to multiplication and division, they work similarly. That is similar, multiplication and division similar to each other, not to addition and subtraction. But for example, let's say we want to multiply 2 decimal numbers. For example, these 2. Now we can just transform these to integers. So if you can rewrite this as integers, then it will have a normal integer multiplication, and that we can use our multiplication algorithm for integers. And this we can write as an integer in the following way. We just write it as 123 times 10 to the minus 3. So it's just rewriting this one. Doing that for that number in the same way, 456 times 10 to the minus 2. Now we see that we can rearrange this because it's multiplication. So we can write this as this. And here we have 10 to the minus 3, 10 to the minus 2, that's 10 to the minus 5. And this multiplication we can just do using normal multiplication algorithm. So that we can just do it here aside. But I want to do it here and I just write down the answer. So then if I do this using the algorithm, I will get this number. So the point here is now I have transformed my decimal multiplication to a normal integer multiplication. And now I just have to move the decimal sign 5 steps. 1, 2, 3, 4, 5. So this is the technique to do it if you have decimal numbers with finitely many decimals. So how do you do then if you don't have like that? So for example, if you have infinite many, for example, if I want to multiply 1, 2, 3, 3, 3, and 4, 5. Both of them could be infinitely many, but let's just take one. And the technique is the same. Now we have seen the technique how to transform this into a fraction. So we say the technique to transform it into a fraction. And the technique was to multiply this to the start of the sequence and at the end of the repeating sequence. So this repeats itself. It repeats itself after 1 here. So we have to move the decimal there, and then we have to subtract, and we can work out our fraction like that. And yet, doing as we did before, you can write this as 111/90. So this is just using technique to write this as this. We won't do the steps here, but and this one we can just write directly as a fraction, since it's only a finite number of decimals. And now it's easy to multiply this, because now we have a fractional multiplication, and we only have to multiply up and down. So what will this be? Here we can now use the multiplication algorithm since we have integers, and if we do that, we will get the answer of 4,995, and this is just 900. And now we can use the division algorithm since these are integers, so we can arrive at the answer. So we can of course answer like this. We don't have to answer as a decimal number. So this is the answer. But let's say that we want to answer as a decimal number. And that we can do by using the division algorithm. And if we do that, we will come to the answer of 5.55. So this is technique for how to do it if we have finitely many decimals or infinitely many where they repeat itself. You say it takes some time to do it like this, but the important point here is how to do it, how to do it in principle. Of course, we can just use a calculator, but we want to understand how we can do it without using a calculator. So how you can multiply decimal numbers. Now there's one case remaining if we have, for example, irrational numbers. For example, let's say that we want to multiply two irrational numbers. For example, pi times square root of 2. Both of these are irrational. And if we write these as with decimals, there will be infinitely many decimals. These 3, 1, 4, 1, 5, and continuing. And this is 1.4142 and continuing. And they will not repeat itself. So here we can't use this technique of writing as a fraction because it's not possible, because they are irrational. So how should we do then? Yeah, in practice, what we can do is that we start to we round off to a certain number of decimals. So for example, we take 314 this and round this off to 141. And now we know how to rewrite these as fractions, since there's only finite many decimals. I can write it like this. And this we have already seen how we can do without only using integer multiplication algorithm and integer division algorithm and the rule for fraction. So this we know how to do. So after I calculated this one, we will get an answer here. Skipping the steps, we will get this. But let's say we want it even more accurately. So we round off to 3 decimals instead. And this will become like that if we round off to 2. There are more decimals here, so it's close to 2. And this is 1414. And again, we do the same way. And if we do this multiplication using fractional multiplication, integer and division algorithm for integers, it will take some time, but it's straightforward, and we will arrive at this. But now we see if we continue this fashion, adding more and more decimals. For example, if we come to the step where we have taken this many decimals. And then the answer will be doing it in the same way. The point here is we see that this sequence starts to stabilize itself. It starts at 4.42 and then 4.44. Then we see here, after doing this for a while, you will see that the first digits in the decimals here will start to stabilize. So they won't change that much. So after a while we go more and more close to the real number that we want. So now we can be pretty sure of these numbers here. And just increasing the number of decimals we have, we get more and more decimals we are sure of. So in this way we can work out how this product will be exactly. So this is a practical how to do it in practice to multiply 2 decimal numbers, irrational numbers. And then we can of course do division. So let's say we have this. But now it's nothing new. It's just the same thing as we had for multiplication. We're using the same techniques. So this we can rewrite as 123 divided by 100. This is 45 divided by 10. So we write this as fractions, since we only have a finite number of decimals. So now we will have fractional division, and that we know how to do. So just flip the second fraction. And this one here now we can do as normal. Of course we can simplify here, but let's just not do that right now. These two now in the numerator and denominator we can do as normal multiplication of integers. And that we can use the algorithm for that normal way. And then we can do the division algorithm for integers. So this you can just work out in the normal fashion. In the same way we can do, for example, if we have infinitely many decimals repeating itself. Then we know just how to rewrite this as a fraction. So writing this as a fraction and this as a fraction, and then we do the same way. So there's nothing new there. And then, again, for example, if we have this instead, have irrational numbers. But it's exactly the same technique as we had for pi times square root of 2 if we multiply. We just round off to a certain number of decimals. So for example, we start 2 decimals Then we work this out in normal way. This here we do in the same way as here, and then continue. Then we get the answer with some decimals, and then we increase the number of decimals, and it will stabilize itself, the sequence, and we will get the answer. So if you know how to do multiplication, all this division is nothing new. It's the same technique, basically.